In the last two lectures, we learnt about the concept of a unit cell and what a primitive and a conventional unit cell is. And during these lectures, we kept referring to points in space. We said that on each we talked about points and which can be atoms or molecules. Now, in today's lecture, I am going to formalize this discussion of points, and in formal language this is referred to as a Bravais lattice. So, today's lecture and the next lecture will also be focused on Bravais lattice. So, let us go to a Bravais lattice. What is a Bravais lattice? So, a lattice, and a lattice is an infinite array of points in space. So, any arrangement of points in space, any ordered arrangement of points in space is referred to as a lattice. Okay. Now, for a Bravais lattice, the arrangement and orientation should be identical for each point. So, whichever point you sit and you look from, you should see the same arrangement and orientation. Okay. So, let us look at some examples. Okay. So, and again I will be using 2-dimensional space to show an example, but you can do the same in 3 dimensions. So, let us construct an array of points. So, let us take one set of points. So, it has to be an ordered arrangement of points. So, this is an arrangement of points, and so you arrange all these points in a line. Then let us say you arrange some points here. This is an ordered arrangement of points, and notice that each point is completely identical. That means, if you sit on any point, you see exactly the same thing. So, if you sit on this point, you will see it has neighbors in this direction, neighbors in this direction, and some additional neighbors in this direction. Okay. And you see the orientation is also identical. Okay. So, this is an arrangement of points. So, this is a Bravais lattice. This is a Bravais lattice. I will use BL for short, Bravais lattice. Now, let us take another arrangement of points, another ordered arrangements where the orientation is not identical, and an example of this is the hexagonal lattice. In two dimensions, if you take a hexagonal lattice, okay, so you take one hexagon, you take another hexagon, you translate, you take another hexagon, you keep doing it in all directions. Okay. This is, and on this side you have this hexagon. So, it looks like this. This is referred to as a honeycomb lattice in 2 dimensions, and you have seen the structure in the honeycombs of bees. Okay, let me, I will just for reference, I will draw some lines connecting these points, so that you can see what the hexagonal honeycomb lattice is. So, this honeycomb lattice in 2 dimensions, okay, it is an ordered arrangement of points, and you can see that the points are it is an infinite arrangement. You can extend this to infinity, and you get this arrangement of points. Now, this is not a Bravais lattice. This is not a Bravais lattice, and the reason it is not a Bravais lattice is the following. If you sit on this point, okay, and you look at the arrangement of points around it, and I will show it over here. So, if you this point, you will see that there is one point directly below it. So, that is shown here. There is one point that is in this direction, and there is another point in this direction. So, this is the arrangement like a Y. Now, if you do the same thing at let us say you do at this point, okay, what you notice is that you have this point. Now, you have a point above it and 2 points. So, it is like an inverted Y. Okay. So, the arrangement of points, the orientation around these 2 points is different, okay, and therefore, this is not a Bravais lattice. Okay. So, the orientation is different. Okay. So, a honeycomb lattice in 2 dimensions is not a Bravais lattice. Now, in 3D space, you can write the Bravais lattice positions in terms of primitive translation vectors. Okay. So, the Bravais lattice positions are expressible. So, if R refers to a Bravais lattice position, that means it is one of the points on the Bravais lattice. It is the coordinate of one of the points on the Bravais lattice. Okay, so, it is the 3 dimensional coordinate of one of the points on the Bravais lattice, and n1, n2, n3 are integers. Okay, are integers. So, that means they are so that means they can be 0, plus or minus 1, plus or minus 2, and so on. So, they can be any positive or negative number, okay, or they can be 0. Okay. Now, so you can write any lattice position in terms of these primitive translation vectors, okay, and you can easily see, suppose you have a simple cubic lattice, in 3 dimensions, okay, then you can choose. So, if you have a simple cubic lattice of size A, and let us say the length of this lattice is A, then I will just complete the cube and imagine that you have a lattice. So, this is really extending in all directions. So, it is extending in the 3 coordinate directions. So, it is along x and so on. Okay, I won't bother drawing the whole thing, but you can easily see that if I take lattice translation vectors like this, and like this. Okay, so, along the 3 coordinate directions. So, my lattice translation vectors A will be equal to A into 1, 0, 0, that is along the x axis. So, in other words, I can write this as A I plus B j plus C k, where I, j, k are unit vector. Oh, A I plus A I can just write it as A I, there is no j and k. So, I is a unit vector along the x direction. Similarly, the lattice translation vector B looks like A 0, 1, 0. This is for a simple cubic lattice, only for a simple cubic lattice, and I can write this as A times j. So, keep in mind we are considering a simple cubic lattice of size A. That means the dimension of the size, the lattice parameter is A. Okay. And C looks like A times 0, 0, 1, or I can write it simply as A times k hat, where k is a unit vector along the z direction. So, now this quantity A is referred to as the lattice parameter, and we can see that in a cubic lattice there is only one parameter. So, the simple cubic lattice has only one lattice parameter. Okay. Now, what is important is that you can write any point as a linear combination of these vectors, and that is very easy to see in the simple cubic lattice. So, if you have any point, it will be either some linear combination of these, where some integral linear combination of these. Okay, and we will look at this more closely. Okay. So, let us look at the primitive translation vectors. So, let us take an example, and I will take 2D as an example, because you can see that 3D is not very easy to draw. So, let us take a lattice that looks, and I will take a lattice. I won't take a square lattice. I will take a slightly, I will take an oblique lattice. So, these are the points on the oblique lattice, and that should be sufficient. Okay. Now, I can take one choice of primitive lattice translation vectors is this. I take this as A. Now, I have only 2 primitive translation vectors, since I am looking at a 2D lattice, and let us say I take A and B as my lattice translation vectors. Let me call it A1 and B1 just for convenience. Okay. Now, you can see that any point. So, if I take let us say I take this point, okay, I can write it as 1, 2, 3 times A plus B. So, this I can write it as 3 times A plus B. Okay. So, it is written exactly as an integer linear combination of these primitive translation vectors. Okay. Now, I said that this combination is not unique. Okay. So, what is meant by that? Okay. So, let me take exactly the same thing, okay, but I will choose 2 different, I will take a different choice for the translation vectors. Okay. So, let me take, let us be a little extreme, let us take this, and let me take this. Okay. So, in this case A remains the same. So, or I should use A1 and B1. Okay. In the first case I had A1 and B1. Okay. Now, I have A2 is same as A1, but B2 is not the same as B1. Okay. And in this case I can write the same point as 2 A2 plus B2. Okay. And you can see this, let me use a different color. So, let me use the violet color. So, you can see that if I do this plus this plus this. So, you can clearly see that A2 plus A2 plus B2 gives you this lattice point. Okay. And I should mention that this is the origin. So, the origin is same as 0 A1 plus 0 B1 or 0 A2 plus 0 B2. Okay. So, you can see that the primitive lattice translations are not unique. Okay. So, you can express them, and you can write as you can choose, I can choose either A1 A2 as the primitive translation vectors, or I can choose A2 B2 as the primitive translation vectors. Okay. And what is important is that the set, I mean the lattice is actually infinite. Okay. So, lattice is infinite. So, the points extend everywhere in space. Okay. The other thing to keep in mind is that since the lattice is infinite, points that might look different are actually identical. So, let us take a very typical example. You take an FCC lattice. So, FCC is actually a lattice, and if you take this FCC lattice, now you might be tempted to say, let me draw the FCC lattice. So, I have a cube, you have a cube, and you have all its face center points. So, and you have all the face centers. So, let me draw the face centers in a different color. So, these are the 6 face centers. So, imagine you have a lattice, you have a set of infinite points where infinite cubes and their face centers. Okay, this is the back face. Okay. So, if you have a now you might think that okay, this corner point, the corner of a cube. So, you have the corner of the cube, the point in black, and the face center which is shown in blue, and you might naively think that these 2 points are actually different. Okay, one is a corner, one is a face center. However, if you keep in mind that the lattice is infinitely extended in all directions, okay, we will just extend, and I will show this by extending the blue points which are the face centers. So, if you take this blue, if you take this blue point and you have a blue point on the neighboring unit cell, okay, it will appear at this point. If you take a blue point on the neighbor of this blue point, it will appear somewhere here. This blue point on this neighboring cell will, let me draw the cube. Okay. So, this blue point will be at the center of this face. Okay. Now, you have a blue point that is in the center of this face, okay, and in the center of this front face, and that I will show it here. And you have a blue point that is center of the rear face, and that I will show it here. Okay. Now, you can see this, that if I take these blue points, if I take this blue point, connect it to a blue point in the neighboring face, neighboring cell, and make this connection. Okay. And now, you also keep in mind that there will be a cell behind this, directly behind it. Okay. And you can see what I am trying to say, that if you take all these points, okay, there will be another cell behind this and cell behind this. You will take all these blue points from the cells, and it will appear that there are the corners. Okay. And now, the black points are actually they appear to be at the face centers. So, the black points which are originally the corners, so that is most easily seen here. So, you can see that this point, okay, now appears like a face center point. Okay. So, the point is just by shifting the cube a little, a point that was at the corner of the cube now becomes a face center. Okay. What we are trying to say is that whichever point you sit on, okay, you will see the same orientation, okay, and you can convince yourself. So, you look around this point, you will see 4 neighbors along these directions. You look around this point, you see 4 neighbors, 4 in plane neighbors. So, essentially all the lattice points are identical, okay, even though they appear to be different. And in fact this is the definition of the Bravais lattice. Okay. You can also verify this for the BCC case. For the BCC lattice also you can verify that all the points are identical. So, there is no difference between the corner point and the body center point. And as I said, you can use many different primitive lattice translation vectors to describe the point. So, let me just show you the primitive translation vectors for an FCC lattice. So, if you have an FCC lattice, and I will draw it again, and I will draw it slightly bigger here just to illustrate the point. So, one choice I can take is the following. I can take point, I can take this choice, I will show it in green. So, one would be this, and so I can take 2 others. Let me take this, and let me take a third one along this. okay, and you can show that any point can be written as a linear combination of these points. Any lattice points can be written as a linear combination of these points. Okay, this is one choice. You could take other choices also. Okay, so what is, you could take many other choices. What is important is that A, B and C should not lie in a plane. Okay, and you can convince yourself that if you make sure that these, so to construct your primitive translation vectors, you can just take translation vectors. Okay, when I say translation vector, I mean they go from one lattice point to another lattice point. Okay, so you can take translation vectors and you take any three translation vectors that do not lie in a plane, and they can be lattice translation vectors. And what you mean is that you can write any lattice point, any Bravais lattice point, which is denoted by R, as N1A plus N2B plus N2C. Okay. So, for example, if using these lattice translation vectors, if you wanted to express this point on the other corner, okay, then you can see that that you can translate it. You can see that let me give names to these. So, let me call this A, B and C. Okay. Then yes, so you can see that this can be written as so I'll show it in a slightly different color. So yeah, I can write this as 2A. Okay, so if I take 2A, then I'll get somewhere here. Okay, and if I take 2C, okay, 2C gives me this. Okay, and if I add these two, you can see that you will end up in a corner that is one. You will end up in the corner of the neighboring cell. So if I take 2A, I'll end up here. Now if I take 2C from here, so C takes along this side face. So now this will be of the neighboring cell. So it will leave you, it will take you to this point 2C. Okay. So this is 2A plus 2C. It will take me to the point on this neighboring cell, on the cell that is directly behind, and then I bring it back here. So that is minus B. Okay. So 2A minus B plus 2C will correspond to this point. So this point, and let me show it in orange, okay, is 2A minus B plus 2C. And you can write any lattice point in a combination of these primitive translation vectors. Okay. Now what is a primitive unit cell? A primitive unit cell, and let me emphasize that here we are referring to the primitive unit cell of the Bravais lattice. Okay, so of the Bravais lattice. So we are referring to the primitive unit cell of the Bravais lattice. This is a volume of space that when translated through all the Bravais lattice vectors, it fills the space without overlaps or voids. Okay. It should fill the space without overlap or voids. Okay. And what that means is that it should contain exactly one point, because if you take all, if you make all translations, then you should get all the Bravais lattice points. Okay. And so the number of translations that you have, okay, it should be as many as the number of lattice points. Okay. And so the number of primitive cells that you should have should be the number of Bravais lattice points. So therefore each primitive cell should contain exactly one lattice point, and again the choice is not unique. Let us look at an example just to be just to get things clear, and let me take the example of a square lattice. So in 2D, again I am working in 2D just because it is easier to represent on the screen. So, if we take a square lattice in 2D, okay, and you imagine that imagine that I have a primitive cell. I'll show at least 3 different ones. So, this can be a primitive cell. Okay. This contains exactly 1 point. Okay. You can see that each of these lattice points contributes 1/4 to this cell, because they are part of 4 of these cells, and you can see that if you translate it. So, if I take this cell and translate it by multiple of the primitive translation vectors, then I will fill up the entire space, okay, and I will fill it up without any voids or any vacancies or any overlaps. So, it fills up the space without voids or overlaps, and you can see this quite easily. So, this is one choice. Okay. Now, let me show you another choice, and I will just extend the lattice here just to illustrate that choice. Now, let me take a cell that looks like this, and you can see that if you extend it, you again fill up space without any voids or overlaps, okay, and you can again see that you fill up the space without any voids or overlaps. Okay. You can make things more, I mean, these are, it looks, you do not have, your cell does not have to be square. Okay. You can take different shapes of cells. For example, let me take a shape. Let me take something like this. Okay. And again you can see that if I take the same cell shape and I translate it here, okay, then I translate it downwards, okay, and so on. Okay, and I can again fill up space without any voids or overhangs. So, I can translate it either to the side or vertically. Okay. So, the choice is not unique. Okay. Now, there is a nice relation between the between the lattice translation vectors and this primitive unit cell. Okay. Now, it turns out that since the primitive cell contains exactly 1 point, okay, you can define these primitive translation vectors. So, you can define primitive translation vectors. So these are special primitive translation, and I will just illustrate these here. Okay. So, these are, let us say here, this is an example. Okay. You can use the same one for this also. Okay. And the idea is that if you had this, if you have these primitive translation vectors, okay, then you can get the size of the primitive cell by looking at the space enclosed by these. Okay. So, in 2D, okay, you need the area enclosed by A and B. Okay. So, that will give you the area of the unit cell, area of primitive cell, primitive unit cell. Okay. So, the area of the primitive unit cell will be given by the area enclosed by these special translation vectors. So now these are not arbitrary lattice translation vectors, these are some specific translation vectors, okay, which help you define the area of the primitive unit cell. In 3D, so I will write it right here. So, in 3 dimensions, okay, you need the volume enclosed by, now you have three vectors A, B, C, okay, and this volume is the volume of the is equal to volume of primitive cell. Primitive unit cell. And what is important is that this is a volume that contains exactly one point. Okay, this is a volume that contains exactly one point. So if you take the volume of the primitive cell, I can write it as A dot B cross C. This is the volume of the primitive unit cell, and this is the volume that contains exactly one point. Okay. Now, what are the Bravais lattices in 2D? In 2D, there are exactly 5 types of Bravais lattices, okay, and I will just illustrate them. Okay. So they are the square. So the square lattice is where the points exactly form a square. Okay. Then there is the rectangular lattice. And in this rectangular, you can have 2 types of rectangular lattices. You can have what is called this is referred to as a primitive rectangular, but you could also have something called the centered rectangular. This is a centered rectangular, and I do not have to tell you, I mean, the shape of rectangles and so on. Okay, but you can see again that each lattice point is identical. Okay, there are 2 others. Okay, so you have these 3. There are 2 others. One is called an oblique lattice, and we already saw some of these. So here you have you can a set of points, and they are at some angle. So it is an oblique rectangular lattice. Okay, and here you can only have primitive. Okay. Then the last one is a triangular lattice, where you essentially take equilateral triangles. Okay, and you make a lattice with these equilateral triangles. So these are the only 5 types of lattices. Now you might say that, oh, this seems very restrictive, but remember, the oblique lattice can take all kinds of angles. Similarly, you can have rectangles of all kinds of aspect, all different aspect ratio. The other point to note is that we said that the honeycomb lattice is not a Bravais lattice. This is a triangular lattice which looks like a hexagon with a center. So it is like a centered hexagon. Okay, that is in fact a Bravais lattice, and you can easily see that each point is identical. Okay. Now in 3D, it turns out that there are only 14 different types of Bravais lattices. This should be in 3D. Okay. Now these 14 different types of lattices are the triclinic, monoclinic, orthorhombic, tetragonal, rhombohedral, hexagonal, and cubic. And within each of them, there are different kinds. There are primitive, face centered, body centered, or C face centered. Okay. Now we'll discuss each of these in detail in the next class, but you already noticed that there are 7 types. Okay, triclinic, monoclinic, orthorhombic, tetragonal, rhombohedral, hexagonal, cubic. So, this gives you 7 types, and you recall the 7 shapes of unit cells that we learnt. Okay, and this is again related to that. Okay, but each of them, some of them, like you can have a primitive cube, you can have a face centered cube, you can have a body centered cube. Okay, so not all of them can have all these different types, but many of them can have these multiple types. Okay. So, we will start looking at Bravais lattices in 3D in more detail in the next class. Okay. So, in this class I have introduced the concept of a Bravais lattice, and at this point the Bravais lattice is just a mathematical construct. So, it's just a construction of various points in space. Okay. And the only condition is that these points have to be arranged, and their arrangement around each point and the orientation around each point is identical. So, in other words, you cannot distinguish one point from another. Okay. So, in the next class we will look at Bravais lattices in 3D in more detail. Thank you.